In this short module, let us see what happens to polynomials as x goes to infinity. Let p of x equal to an x bar n plus dot 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 a naught, an not equal to 0 be a polynomial that is non-constant, that is not constant. So we are not obviously considering the constant polynomials. We want to study what limit x going to infinity of p of x is. Okay, this is actually going to be equal to infinity. Let's see why this is the case. So you have this an x bar n plus dot 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 a naught. What you do is you take x bar n outside. You get x bar n into an plus a n minus 1 by x bar n minus 1 plus dot 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 a naught by x bar n. Okay. Now we already know that limit x going to infinity of 1 by x is 0. In fact, limit x going to infinity of 1 by x bar k is also 0. Therefore, by extended limit laws, which is part of the exercises, by extended limit laws, we get that this is just converges to x bar n into an as x goes to infinity, which goes to infinity. Okay, so essentially what happens is all these terms become really small, and this term, the leading coefficient x bar n, dominates the entire polynomial, and as x goes to infinity, this goes to infinity. So once you solve the exercises, this proof will become rather trivial. So the upshot of all this is p of x goes to infinity as x goes to infinity. Nice. Now what about p of x as x goes to minus infinity? As x goes to minus infinity. Well, it depends on the degree. If degree is even, then again p of x converges to infinity. Same proof will work. If degree is odd, then p of x converges to minus infinity. P of x converges to minus infinity. This is just again easy proof. What happens is when the degree is odd, the powers will still continue to be negative. Negative power will still be negative, and you will get that p of x converges to minus infinity. Okay, so we have seen now that polynomials behave in an unbounded way as you approach infinity. Now one more comment I would like to make. We have already seen that limit n going to infinity a bar n by n bar k for fixed k, this goes to infinity as a sequence. Now by using the same idea and by using the definitions of limit going to infinity, you can solve this easy exercise. Okay, so limit n going to infinity of x bar n, not x bar n, limit n going to infinity of a bar x divided by p of x, where p of x is a non-constant polynomial, constant polynomial, and let me just change this n to x. X goes to infinity and a is greater than 1. A is greater than 1. This goes to infinity. So exponential goes to infinity faster than any polynomial. So the definition of a power x, if you recall, is via logarithms, which we have not yet seen in rigorous detail, but your high school and even lesser middle school knowledge of logarithms should be more than enough to tackle this exercise. So let me just repeat. For this, you just need to use the various properties of infinite limits combined with what you have already seen for sequences. So please prove this. This is very important. It illustrates the power of exponential growth. Exponentials quickly dominate any polynomial. This is a course on real analysis, and you have just watched limits at infinity of polynomials.